So if you take a single liter of everyday gasoline, like just a standard water bottle's worth of fuel,
Right.
and you completely combust it, you release this very specific amount of thermal energy. But, I mean, what's truly mind-bending here isn't the fire or even the heat itself.
It's what that exact amount of energy is actually capable of doing.
Yes, because if you captured all of that thermal energy
Mhm.
and uh, applied it to a solid block of ice, you could instantly melt 218 pounds of ice into a massive puddle of water.
Which is just a staggering physical reality, honestly.
And here is the real kicker. You could do all of that without raising the temperature of that water by a single degree.
Yeah, the sheer density of energy hidden inside chemical bonds is, well, it's almost impossible to intuitively grasp until you run the numbers.
And running those numbers is exactly what we are doing today. So welcome to the deep dive. If you are joining us, yes, you, the perpetually curious learner who doesn't just want to know that a car moves, but exactly how the universe tracks every microscopic drop of energy required to move it, you are in the right place.
You definitely are.
We are exploring the absolute bedrock of physical chemistry today, thermodynamics. Specifically, we are hunting down a concept known as enthalpy.
Enthalpy is, without exaggeration, the master ledger of the universe.
The master ledger. I love that.
It really is. I mean, when we look at the world around us, we expect visible cause and effect, right? You physically push a door, the door swings open.
Right, it's tangible.
Exactly. But when you step into the realm of chemical reactions, that visible tracking system just vanishes. We're suddenly dealing with an invisible landscape of energy transfers that dictate, well, everything.
From how a storm system forms over the ocean to, why a chemical cold pack instantly freezes in your hands.
Even to how we might eventually replace the entire fossil fuel industry.
Exactly. So our mission today is to completely unpack that hidden ledger. We're going to dive into how heat actually flows on a molecular level, the critical difference between how much matter you have versus what kind of matter it is.
Oh, that is so important.
Right. And ultimately, why the invisible crushing weight of our own atmosphere makes this concept of enthalpy the ultimate master key for engineers and chemists everywhere.
But to understand enthalpy, we really have to start at the absolute foundation. We have to define the currency we're actually tracking.
Right, which in thermodynamics is simply defined as the capacity to supply heat or do work.
Which is energy.
Energy, exactly.
Yeah.
And I know most of us are pretty familiar with the big macroscopic versions of this. Like, we know potential energy is stored energy.
Right, like water sitting perfectly still at the very top of a towering hydroelectric dam.
Yeah, holding all this potential simply because of its high position relative to gravity.
And we also intuitively understand chemical potential energy.
Right.
The atoms inside that liter of gasoline you mentioned earlier, or, the lithium ions inside your smartphone battery, they're arranged in highly specific configurations.
Like tiny, tightly coiled springs.
Exactly. Those molecular bonds act like springs holding immense potential energy just waiting to be unleashed.
And when that energy is unleashed, like when the water falls through the dam or the gasoline ignites, it becomes kinetic energy.
The energy of active motion.
Right. The water spins a massive physical turbine. The expanding gas pushes a heavy metal piston in your car. That's macroscopic work.
But where things get really fascinating for our purposes today is when we zoom all the way in.
To the microscopic level.
Yeah, because kinetic energy isn't just a car driving down the highway. It is also thermal energy.
And this is a really crucial distinction, isn't it?
It absolutely is. Thermal energy is the kinetic energy associated with the random, chaotic motion of atoms and molecules.
So even if you were looking at a solid iron anvil sitting perfectly motionless on a workbench,
At the molecular level, it is not still at all.
its iron atoms are constantly violently vibrating in place.
They're buzzing.
Buzzing.
Yeah.
And the faster they vibrate, the higher the thermal energy. Which actually brings us to a massive foundational rule we have to establish before we go any further.
The first law of thermodynamics.
The law of conservation of energy.
Right. The cosmic rule that energy can never be created out of nothing, and it can never be destroyed into nothing.
It just changes outfits.
Essentially, yes. It can only ever be transferred from one place to another or transformed from one type to another.
So when that gasoline combusts inside a car engine, that chemical potential energy doesn't just vanish into the ether once the reaction is done. Every single fraction of a joule is accounted for somewhere.
A portion of it becomes the mechanical kinetic energy that physically turns the wheels of the car.
Right.
And the rest of it becomes thermal energy. It heats up the engine block.
But if you were to add the mechanical work and the heat together, they would perfectly, exactly equal the chemical potential energy of the original unburned fuel.
The ledger always balances perfectly to zero. It has to.
It has to. But to track that ledger accurately, I feel like we have to clear up a major linguistic hurdle here.
Oh, definitely. We have to violently separate two words that almost everyone uses completely interchangeably in daily life.
Temperature and heat. This is so important. If you mix these two up, the rest of the thermodynamics we're going to talk about just totally falls apart. So let's look at temperature first. Temperature is strictly a quantitative measure. Right.
It is essentially a speedometer for that microscopic kinetic energy we just talked about.
Okay, a speedometer.
Precisely. If the molecules of a substance are vibrating frantically, meaning they have a very high average kinetic energy, we look at our speedometer and say the substance has a high temperature.
It is hot.
Right. And if they are vibrating sluggishly, low average kinetic energy, the speedometer reads low. It is cold.
Okay, so temperature is the gauge. But heat, which, by the way, in thermodynamics is always symbolized by a lowercase q, is an entirely different beast.
It is. Heat is the actual transfer of that thermal energy between two bodies that are currently at different temperatures.
Okay, so temperature is the state of being, but heat is the action of moving.
Yes, that's a great way to put it.
Let's try to visualize this. Imagine thermal energy is this massive, chaotic mosh pit at a heavy metal concert.
Okay, I like where this is going.
So temperature is just a drone flying overhead.
Right.
It's just calculating the average speed of the people slamming into each other.
Some people are sprinting, some are just bouncing.
Exactly. But the drone just gives you an average speed. That's the temperature. Now imagine that frantic mosh pit is surrounded by a crowd of people who are just standing perfectly still, holding their drinks.
A great visualization. And what happens at the boundary where the moving pit meets the stationary crowd?
Well, the people flying around in the pit are going to violently crash into the people standing still. They literally physically transfer their kinetic energy through that collision.
Right.
The person standing still suddenly gets shoved backwards. They are now moving, and the person who bumped into them loses some of their momentum, so they slow down. That physical transfer of kinetic energy across the boundary, that is heat.
That is Q. And that mosh pit analogy perfectly illustrates the only direction heat can ever flow.
Because it only goes one way.
Always. The fundamental rule is that heat always spontaneously flows from a substance at a higher temperature to a substance at a lower temperature.
So the stationary crowd cannot magically transfer momentum to the people already sprinting.
Exactly. The energetic molecules literally have to collide with the sluggish molecules to pass the energy along.
So if you drop a blazing hot piece of iron into a bucket of cold water, the frantically vibrating iron atoms smash against the relatively sluggish water molecules,
And the iron atoms lose some of their vibration, so the iron's temperature drops.
while the water molecules gain that kinetic energy and start vibrating faster, so the water's temperature rises.
And this transfer relentlessly continues until they reach what we call thermal equilibrium.
Right, so the mosh pit has completely equalized. Everyone in the entire room is now bouncing at the exact same average speed.
Both the iron and the water end up at the exact same final temperature. And once their average kinetic energies match, the massive net transfer of energy, the heat flow, the Q, stops entirely.
That is just a beautiful mechanical reality of how heat flows. But I feel like it immediately raises a much deeper physical question.
What's that?
Well, we know heat flows from hot to cold until things equalize. But does every substance in the universe absorb that flowing kinetic energy in the exact same way? Like, if I pump 100 joules of heat into a block of metal and 100 joules of heat into a puddle of water, do their speedometers, their temperatures spike by the exact same amount?
And the physical reality there is a resounding no. Which brings us to one of the most vital concepts in thermodynamics.
Heat capacity.
Yes. And the strict difference between intensive and extensive properties of matter.
Let's break those properties down because, I mean, they dictate how everything in the physical world is built. So an extensive property, that's a property that depends entirely on the amount of matter you are dealing with.
Exactly. Mass is the classic extensive property. Volume is another one.
So if you have a single drop of water, it has a very tiny mass and takes up a very tiny volume.
But if you have an entire Olympic swimming pool of water, the mass and volume are millions of times larger. The property extends as the amount of matter extends.
Okay, that makes perfect sense. But an intensive property is totally blind to the amount of matter. It only cares about the identity of the matter. It only cares about what the substance actually is.
Density is a perfect example of an intensive property. A single drop of pure water and an entire Olympic swimming pool of pure water have the exact same density, roughly 1 gram per milliliter.
The identity of the substance dictates the property, not the scale.
Right. So how does this apply to our mosh pit? How does this apply to absorbing heat?
Yeah, how does it?
It applies through two closely related but fundamentally different measurements. The first is specific heat capacity.
Which is usually just called specific heat. Right?
Yes, and represented by a lowercase c. Specific heat is an intensive property.
Okay.
It is the exact amount of heat energy required to raise the temperature of exactly 1 single gram of a substance by exactly 1 degree Celsius.
So it's basically a baseline measurement for the material itself.
Exactly. Let's look at cast iron. Whether you are holding a tiny cast iron ball bearing that weighs 1 gram or a massive cast iron anvil that weighs 100 kilograms.
The specific heat of iron is the same.
Always. It's 0.449 joules per gram per degree Celsius. It is intensive. It is a fundamental fingerprint of iron atoms.
Okay, but if I actually want to heat up that anvil, I can't just use the intensive property, right? Because I have a lot more than 1 single gram of iron to heat up.
Precisely. And that brings us to the extensive counterpart, overall heat capacity, represented by a capital C.
Capital C.
This is the total amount of heat required to raise the temperature of the entire object by 1 degree.
Okay, let's put some numbers to this to make it concrete.
Yeah.
Let's say you have 2 cast iron frying pans in your kitchen.
Sure.
You have a small pan for cooking a couple of eggs, and it weighs about 800 grams. Then you have a massive, heavy-duty camping pan that weighs exactly 5 times as much, 4,000 grams.
Well, because they are both made of iron, their specific heat, the intensive lowercase c, is identical, 0.449.
Right.
But because the massive pan has 5 times the mass, it has 5 times as many individual iron atoms that need to be vibrated faster.
So its overall heat capacity, the extensive capital C, is 5 times larger.
Exactly. It takes 5 times as much total thermal energy to raise the temperature of the massive pan by 1 degree compared to the small pan.
You literally have to push 5 times as many people in the mosh pit to get the same average speed.
That's it exactly. And this relationship forms the absolute bedrock mathematical equation of calorimetry and heat flow. It is the formula Q equals mc delta T.
Q equals mc delta T.
Yeah.
So let's really linger on this equation because it's like the Rosetta Stone for understanding how the physical world handles heat.
It really is. So Q is the total heat energy absorbed or released, measured in joules.
Right, and it equals m, which is the total mass of your object in grams.
Yeah.
The extensive part.
Multiplied by C, the specific heat capacity of that exact material, the intensive part.
Multiplied by delta T. And the triangle symbol delta in physics just means change in. So delta T is simply your final temperature minus your initial temperature.
How much the speedometer moved.
Exactly. And the predictive power of this simple algebraic equation is just astonishing.
Yeah.
If you know 3 of those variables, you can perfectly predict the physical reality of the 4th.
Let's run a real-world scenario with this.
Okay, let's do it.
Let's say you are making dinner and you plug in a standard countertop rice cooker. You pour in 2 cups of water.
Okay, 2 cups is about 437 milliliters. And since the density of water is essentially 1 gram per milliliter, we know our mass is 437 grams.
Right. We know our starting room temperature is about 25 degrees Celsius, and we need to bring that water to a rolling boil at 100 degrees Celsius.
So our change in temperature, our delta T, is 75 degrees.
Yes. We want to calculate Q. How much total heat energy does the rice cooker need to pump into that pot? We have M, we have delta T.
And the last piece of the puzzle is C, the specific heat capacity of water. And this is where the universe throws us an absolute curveball, doesn't it?
Oh, it is one of the most miraculous molecular quirks in nature.
Because we established that the specific heat of iron is 0.449 joules. And most metals sit well under 1 joule. Like gold is incredibly low, at 0.129 joules to heat up 1 gram by 1 degree.
But liquid water,
Yeah.
the specific heat of liquid water is a massive 4.184 joules per gram per degree Celsius.
Wow. It requires an extraordinary amount of energy to make water molecules vibrate faster.
It does.
But why? I mean, if they're just molecules, why is water so incredibly stubborn about heating up compared to a block of iron?
It comes down to the architecture of the water molecule itself. H2O.
Okay.
Oxygen is a highly electronegative atom, meaning it aggressively pulls electrons toward itself, leaving the two hydrogen atoms slightly positively charged.
This creates a dipole, a
Mhm.
tiny magnet, essentially.
Yes. So the slightly negative oxygen of one water molecule is highly attracted to the slightly positive hydrogen of a neighboring water molecule.
We call these hydrogen bonds, right?
We do. And in liquid water, these hydrogen bonds act like millions of incredibly stiff, microscopic shock absorbers linking all the molecules together.
Oh, I see.
So when the rice cooker pumps thermal energy into the water, that energy doesn't immediately translate into the molecules flying around faster, which is what would raise the temperature.
Right.
Instead, massive amounts of that incoming energy are absorbed simply stretching, bending, and fighting against those stiff hydrogen bond shock absorbers.
It's literally eating the energy. The water acts like a colossal thermal sponge.
Exactly. It can soak up vast amounts of heat before its internal speedometer as temperature actually starts to climb.
Let's finish that rice cooker math
That's
to
like
see
that.
just how much. So we have 437 grams of water multiplied by water's specific heat of 4.184 multiplied by a temperature change of 75 degrees.
Right.
To boil 2 measly cups of water for dinner, the rice cooker has to generate over 137,000 joules of heat energy.
It's a massive energetic cost. But, this exact molecular quirk, this thermal sponge behavior, is the primary reason life on Earth hasn't been eradicated.
Oh, absolutely. I mean, this perfectly explains the classic summer day paradox.
You mean the hot car?
Yes, you get into a car that has been baking in the direct July sun for 6 hours. You touch the metal seatbelt buckle, and it is so hot it physically sears your skin.
Ouch.
But you reach down and grab a plastic bottle of water that has been sitting in the cup holder in that exact same car for the exact same amount of time, absorbing the exact same solar radiation.
And the water is just, unpleasantly warm.
Exactly. The metal buckle, with its very low specific heat, had no shock absorbers. Every joule of solar energy it absorbed immediately violently vibrated its atoms, spiking its temperature.
While the water, with a specific heat 10 times higher than the metal, soaked up that exact same solar energy but used it to bend its internal hydrogen bonds.
Its temperature barely budged.
And scale that up to the global level. The Earth's oceans are a planetary-scale thermal sponge. They absorb unimaginable amounts of solar radiation every single day.
Which is terrifying to think about if they weren't made of water.
Right. If the oceans were made of a low specific heat liquid, they would literally boil away under the summer sun and freeze solid at night.
Instead, they just gently absorb the heat, regulating the entire global climate.
It is all perfectly predictable through Q equals mc delta T, but this thermal sponge behavior leads us to a necessary threshold.
What happens when the sponge is full?
Right. We know water can soak up heat while its temperature climbs from 25 to 50 to 90 up to 100 degrees Celsius. But what happens the exact moment it hits 100 degrees?
Yeah, if you keep the rice cooker turned on, pumping thousands of joules of heat into the water, the temperature stops rising. It just halts at 100 degrees while it boils. Where is all that heat going if the speedometer stops moving?
To answer that, we really have to look at the strict directionality of heat flow during what we call phase changes. And we need to define two major thermodynamic terms.
Exothermic and endothermic processes.
These are fundamental. Let's start with exothermic. Exo meaning outside, thermic meaning heat.
So an exothermic process is a chemical or physical change that releases heat out into its surroundings.
A classic visceral example is using an oxyacetylene torch to cut through a steel beam.
Oh, yeah.
When you ignite acetylene gas in the presence of pure oxygen, you are breaking the carbon-carbon triple bonds of the acetylene and forming entirely new, highly stable bonds to create carbon dioxide and water vapor.
And the energy stored in those original acetylene bonds is vastly greater than the energy needed to hold together the resulting CO2 and water.
Exactly. So the universe has to balance the ledger. That massive excess of potential energy is violently ejected into the surroundings as thermal energy, heat, and blinding light.
It is highly exothermic.
It pumps so much kinetic energy into the surrounding steel beam that the steel atoms vibrate violently enough to break their solid structure and melt.
Heat aggressively flows out. But then we have the exact opposite, endothermic. Endo meaning inside. An endothermic process is a change that actively absorbs thermal energy from its surroundings. Heat flows in.
Think about the instant chemical cold packs you keep in a first aid kit for a sprained ankle.
Right. They don't need to be kept in a freezer. They just sit at room temperature.
Exactly. Inside the plastic sleeve is a pouch of water, and surrounding that pouch is a dry chemical salt, usually ammonium nitrate.
And when you punch the pack and break the inner water pouch, the solid ammonium nitrate salt mixes with the liquid water.
And the process of that solid salt dissolving into the water is highly endothermic. Let's look at the molecules here. To dissolve that salt, you have to physically tear apart the rigid, highly ordered crystalline lattice of the solid ammonium nitrate.
You have to separate the positively charged ammonium ions from the negatively charged nitrate ions.
Pulling apart magnets takes work. It requires energy.
Precisely. The act of breaking those ionic bonds requires a significant input of thermal energy.
Now, when the water molecules surround those free-floating ions to form hydration shells, some energy is released, but it is not nearly enough to cover the massive energetic cost of breaking the solid lattice in the first place.
So the reaction is operating at a massive energy deficit.
Yes. So the reaction literally acts as a thermal vacuum. It pulls the necessary kinetic energy out of whatever is closest. First, it drains the thermal energy from the water inside the pack, causing the water's temperature to plummet toward freezing.
And then, when you place that pack against your swollen, sprained ankle, the reaction begins pulling thermal energy directly out of your muscle tissue.
It is vital to realize here that the pack is not generating cold.
Because cold isn't a thing.
Right. Cold is not a physical substance that can be created. Cold is merely the absence of heat. The chemical reaction in the pack is an energy thief.
An energy thief.
It is forcefully vacuuming the kinetic energy out of your skin to fuel its own dissolution. You feel a sensation of cold because your thermal energy is rapidly draining away.
That is wild. The universe forcing your own body heat to pay the chemical debt of a dissolving salt. Okay, so how does this endothermic vacuum effect answer our boiling water question?
Because a phase change, like melting solid ice into liquid water or boiling liquid water into a gas, is an entirely endothermic process.
Okay, let's walk through the melting of ice, because this completely exposes the hidden ledger.
Okay.
You take a solid block of ice out of a freezer. It is sitting at exactly 0 degrees Celsius. You place it on a hot stove.
Yeah.
You are aggressively pumping thermal energy Q into the ice.
But if you stick a thermometer into the slush, the temperature does not rise to 1 degree.
It stays locked at exactly 0 degrees Celsius. The scudometer is completely stuck, even though the mosh pit is being aggressively pushed. Why?
Because of what we call latent heat.
Hidden heat.
Yes. Remember those stiff hydrogen bonds holding the water molecules together?
But shock absorbers.
Right. In solid ice, those bonds are locked into a rigid, highly structured crystal lattice. When you add heat to that ice, the energy does not go toward making the molecules vibrate faster, which is what would raise the temperature.
Instead, 100% of that incoming thermal energy is immediately spent doing the brutal physical work of breaking the lattice apart.
Exactly. It is tearing the water molecules out of their rigid structure so they can flow freely as a liquid.
So the energy is entirely consumed by the phase change.
Yes. Only after every single microscopic crystal of ice has been destroyed and the entire mass is 100% liquid water, will the incoming heat finally be allowed to make the liquid molecules vibrate faster, causing the temperature to rise above 0 degrees.
And this brings us right back to that terrifying calculation from the very beginning of the deep dive.
The gasoline.
Yes. The amount of hidden, latent heat required to force these phase changes is just astronomical.
It truly is. To return to the text example, combusting just 1 single liter of isooctane, a primary component of standard gasoline.
Right. Burning 1 water bottle's worth of gas is a highly exothermic reaction that releases 33,100 kilojoules of heat. That is 33 million joules.
And because it takes 334 joules of latent heat to melt a single gram of ice.
If you applied all 33 million joules from that 1 liter of gas directly to a block of ice at 0 degrees,
you would perfectly, cleanly break the lattice bonds of 99.2 kilograms of solid ice.
218 pounds. You melt a block of ice the size of a professional linebacker into a puddle of water, entirely through latent heat, without the water ever getting warmer than 0 degrees Celsius.
It's hard to wrap your head around.
It's the sheer brutal magnitude of chemical potential energy stored in the hydrocarbon bonds of fossil fuels.
And it perfectly illustrates the relentless accounting of thermodynamics. The energy is never lost. It simply changes form from chemical potential to flowing heat to the physical and mechanical work of tearing apart a crystal lattice.
Which brings us to the absolute core of our exploration today.
Great.
We have tracked heat moving between frying pans and soaking into water and melting ice. But in all of these scenarios, we've kind of just assumed we are tracking pure heat in a vacuum.
Which isn't how reality works.
Right. Real chemistry, whether it's happening in a beaker on a lab bench or in a car engine or in your own biological cells, doesn't happen in a vacuum.
No, it happens out in the open. It happens while pushing against the crushing, invisible weight of the Earth's atmosphere.
And to accurately mathematically account for energy transfers in the real world, tracking just the heat isn't enough. We have to introduce the ultimate thermodynamic concept. We have to talk about enthalpy.
And to understand why enthalpy is so incredibly necessary, we first have to introduce a broader baseline concept called internal energy, mathematically represented by a capital U.
Internal energy. What exactly goes into U?
Well, internal energy is exactly what it sounds like. It is the grand total, the complete reservoir of every possible kind of energy present inside a substance.
Everything.
Everything. It is the kinetic energy of its frantically vibrating atoms, the potential energy stored in its chemical bonds, the rotational energy of its molecules tumbling over each other. If you sum up every microscopic whisper of energy in the system, that grand total is U.
Okay, so a system sits there with its total U, but we're interested in changes, right?
Yeah.
We want to know what happens when a reaction occurs. And the formula for the change in internal energy is beautifully simple. Delta U equals Q plus W.
Yes. The change in a system's internal energy is equal to the heat flow, Q, plus the work done, W.
This makes logical sense. If heat flows into my system from a Bunsen burner, my internal energy goes up. If my system is highly exothermic and blasts heat out into the room, my internal energy goes down.
That's the Q half of the equation.
Right.
But is the W the work that makes reality so complicated? When we talk about work in chemical thermodynamics, we're usually talking about expansion work, also known as pressure volume work or PV work.
PV work. Let's really drill down into what pressure volume work actually physically looks like, because I think this is where thermodynamics loses a lot of people. It's easy to visualize a system getting hotter. It is much harder to visualize a chemical reaction doing work.
Okay, let's visualize the internal combustion engine of a car. You have a heavy metal cylinder. Inside that cylinder is a metal piston that can slide up and down.
Got it.
You inject a tiny amount of liquid gasoline and oxygen into the enclosed space beneath the piston, and you spark it.
The gasoline and oxygen combust. We know this is massively exothermic, so a huge amount of heat Q is violently released.
But the reaction doesn't just release heat. The chemical reaction physically transforms liquid gasoline and oxygen gas into entirely new exhaust gases, primarily carbon dioxide and water vapor.
And at those extreme temperatures, those newly formed gases violently expand. They demand vastly more physical volume than the liquid fuel did.
But they are trapped under the piston, so what do? The rapidly expanding gases physically slam into the underside of the heavy metal piston and forcefully push it upward.
And pushing a physical mass against an opposing force is the exact definition of work.
Yes, the expanding gas is doing mechanical work on its surroundings.
So if we look at our equation, delta U equals Q plus W, the burning gasoline system loses internal energy for two entirely separate reasons. It loses energy by radiating heat out into the cold engine block. And it loses energy by spending its own kinetic force to do the brutal mechanical work of pushing that heavy piston upward.
Exactly. Yeah. The total drop in the gasoline's internal energy, delta U, is the sum of the heat lost plus the mechanical work done.
Okay, I mean, an engine piston is easy enough to visualize, but what if I just burn some fuel out in the open? What if I strike a match on my back porch? There is no metal piston, there is no engine block.
Yeah.
Is the match doing pressure volume work?
Yes, it is doing a massive amount of invisible work.
Invisible work.
Yes. And to understand why, you have to understand what atmospheric pressure actually is. We live at the absolute bottom of a literal ocean of air. The Earth's atmosphere extends roughly 50 miles straight up above your head.
And gravity is pulling all 50 miles of that air relentlessly downward.
Right. At sea level, that 50-mile high column of air exerts a crushing pressure of about 14.7 pounds on every single square inch of your body and every single square inch of the match you just struck.
That is exactly 1 atmosphere of pressure. It is a heavy, relentless, invisible physical weight.
So when I strike the match, the chemical combustion creates hot, expanding carbon dioxide and water vapor gases.
And for those newly born gases to physically exist, for them to expand and claim physical volume in the real world, They literally have to push against that 14.7 pounds per square inch.
They have to physically heave that invisible 50-mile-high column of atmospheric air up and out of the way to make room for themselves.
Wow. So pushing the atmosphere out of the way is the invisible piston.
It is. The expanding gas from the match is doing physical, mechanical pressure volume work against the Earth's atmosphere.
That's amazing. So the match loses internal energy both as the visible heat of the flame and as the invisible mechanical work of pushing the atmosphere out of the way. Delta U equals Q plus W.
Precisely. And this brings up a critical property of internal energy. The math dictates that internal energy is what physicists call a state function.
A state function. This is a vital conceptual tool.
It is. A state function is a property whose total value depends only on the current exact state of the system, regardless of the path taken to get there.
Right. The classic analogy here is climbing a mountain. Let's say you were standing on the exact summit of Mount Kilimanjaro in Africa. Your absolute altitude is exactly 5,895 meters above sea level. That altitude is a state function.
Why? Because you are at 5,895 meters regardless of how you arrived. It doesn't matter if you spent 6 exhausting days hiking up a winding, treacherous 40-mile trail. And it doesn't matter if you strapped on a parachute, jumped out of a helicopter, and fell straight down onto the peak.
Your final state of altitude is identical. The path you took has absolutely zero effect on your current altitude.
Right. Altitude is a state function, but the actual distance you physically traveled to get to the summit, that is not a state function.
Exactly. The hiker walked 40 miles. The skydiver fell 2 miles. For distance, the path matters entirely.
In thermodynamics, internal energy U is a state function just like altitude. The total reservoir of energy in the system only depends on its current state. But heat Q and work rad O are not state functions.
They are like the distance traveled. The amount of heat released and the amount of work done depend entirely on the specific path the chemical reaction takes.
Which brings us finally to the supreme elegance of enthalpy. Because chemists and engineers ran into a massive problem. Internal energy is a great concept, but it's wildly annoying to measure in the real world.
Right. If I am a chemist mixing chemicals in an open beaker on my lab bench, I just want to know how much heat the reaction is going to blast into my face. I just want to know Q. I don't care about the invisible mechanical work the expanding gases are doing to push the atmosphere out of the way.
But if you just try to measure the change in internal energy, delta U, you have a mess. Because delta U includes both the heat and the work. Every time you measure a reaction in an open beaker, some of the energy is stolen to do that invisible atmospheric lifting. So to isolate just the heat, you would have to constantly calculate the exact atmospheric pressure, the exact change in volume, calculate the PV work, and subtract it from the total energy change.
It makes the math a nightmare.
It's an absolute accounting nightmare. So chemists essentially invented a brilliant accounting trick. A new state function that automatically bakes the cost of pushing the atmosphere out of the way directly into the math.
Yeah, the trick is enthalpy.
Yes, enthalpy, represented by a capital H, is defined by a very specific equation, H equals U plus PV. Enthalpy is the sum of a system's internal energy plus the mathematical product of its pressure and volume.
Let's really look at this, because U is a state function, and pressure and volume are also state functions. Enthalpy must also be a state function. It doesn't care about the path.
Correct. But the true genius of enthalpy reveals itself when you do chemistry in the open air. In an open beaker, the atmospheric pressure is constant. It's always 1 atmosphere. It doesn't change.
Because the pressure is constant, when you run the calculus on H equals U plus PV, the math perfectly simplifies. It proves that under conditions of constant pressure, the change in enthalpy, delta H, is exactly mathematically equal to the heat transferred.
Delta H equals Q at constant pressure.
That single equality is the foundation of modern thermochemistry. It means that when you run a reaction out in the open atmosphere, the enthalpy change is literally just the heat you feel.
The mathematical formula of enthalpy automatically, perfectly subtracts the annoying cost of pressure volume work behind the scenes.
So enthalpy isolates the heat. It lets us write clean, perfectly predictive thermochemical equations without ever having to manually calculate the mechanical work of expanding gases.
If you burn a mole of methane on a Bunsen burner, the heat released into the room is the exact delta H of the reaction.
It's basically magic.
It feels like it. Enthalpy is the standardized currency of heat for our normal, constant pressure atmospheric world. But, and this is important, we have to emphasize that it only works at constant pressure.
If you change the environment, enthalpy no longer equals the heat you feel.
And the ultimate example of this is a fantastic piece of lab equipment called a bomb calorimeter.
Oh, a bomb calorimeter.
A bomb calorimeter is a massive, incredibly heavy, rigid steel container. It is specifically designed to safely measure highly explosive combustion reactions.
You place your fuel sample inside a small crucible, seal the heavy steel bomb, pump it full of high-pressure oxygen gas, and trigger a spark to ignite it.
The combustion happens violently, it releases massive amounts of heat, and naturally it tries to create a massive volume of expanding exhaust gases. It wants to do expansion work.
But it can't.
Yeah.
Because the bomb calorimeter is made of solid, rigid steel, the total volume cannot change. The walls literally do not move.
And if the volume can't expand, it cannot do any pressure volume work. The work W is strictly zero.
Exactly. The gases are trapped. Instead of expanding the volume, the massive kinetic energy just relentlessly spikes the internal pressure inside the bomb. Because the volume is constant, not the pressure, the heat measured by the bomb calorimeter does not equal the enthalpy change.
Let's trace the math. If W is 0, then delta U equals Q plus 0.
Right.
So in a bomb calorimeter, the heat U measure is exactly equal to the total change in internal energy, delta U. All of the potential energy had no choice but to become pure heat because doing mechanical work was physically impossible.
Wow. So enthalpy delta H is the heat at constant atmospheric pressure where work is allowed. Internal energy delta U is the heat at constant rigid volume where work is impossible.
It is a phenomenal distinction.
Yeah.
And for enthalpy, we use the exact same directional signs we did for heat flow.
Okay, so if a reaction is exothermic, meaning it releases heat out into the constant pressure world, it loses enthalpy. So delta H is a negative number.
And if a reaction is endothermic, meaning it acts like a thermal vacuum and pulls heat in it, gains enthalpy, so delta H is a positive number.
Which brings us to the final, and really the most crucial, application of this entire deep dive. How do we use this mathematical accounting trick to actually build the modern world?
Right. If enthalpy is this perfect currency for heat, how do we tabulate it? How do we use these values to predict the exact energy output of experimental fuels we haven't even synthesized yet?
Because to tabulate anything in science, you must establish a baseline. You must standardize the environment.
Chemists use standard state conditions. When we report a thermodynamic value, we assume the material is under a pressure of exactly 1 bar, which is essentially exactly 1 atmosphere, and any solutions are at a strict 1 molar concentration.
And usually these tables also assume a standard temperature of 298.15 Kelvin, which is about 25 degrees Celsius, standard room temperature.
Right. When you measure the enthalpy of a reaction under these exact standard conditions, you denote it by adding a little superscript degree symbol to the H. So delta H becomes delta H naught.
And one of the most useful compilations of data we possess is the table of standard enthalpies of combustion. This is the exact enthalpy change measured when exactly 1 single mole of a specific substance is completely burned in pure oxygen under standard conditions.
It is the ultimate apples-to-apples comparison of fuels. You look at the table and it lists isooctane gasoline at a staggering delta H naught of negative 5,460 kilojoules per mole.
Highly violently exothermic. It releases massive heat.
But we aren't just using these tables to look at fossil fuels anymore. We are using thermochemistry to engineer their replacements. One of the most fascinating engineering frontiers right now is algae-based biofuels.
Oh, this is such a cool application. Because as we all know, fossil fuels are finite, and burning them releases ancient carbon that has been trapped underground for millions of years, spiking atmospheric CO2.
We need a high enthalpy replacement that uses carbon already in the atmosphere.
And certain strains of microscopic algae are the perfect candidates for this. Unlike standard crops like corn or soybeans, which spend most of their biological energy building stalks and roots and leaves.
These algae are essentially microscopic oil factories.
They use the biological process of photosynthesis to pull CO2 directly out of the air, and they use the energy of sunlight to synthesize long-chain hydrocarbon lipids, oil.
Up to 50% of their total body weight can be pure extractable oil.
That is insane. And the thermochemical math makes it incredibly viable. They grow incredibly fast. They can be grown in brackish water that isn't fit for human consumption.
And they yield an astonishing 26,000 gallons of biofuel per hectare. That absolutely dwarfs the energy yield of terrestrial crops.
We are literally just using biological organisms to harvest the enthalpy of the sun and package it into dense chemical bonds for us. And the engineering is getting cheaper. I mean, the U.S. military is already producing aviation jet fuel from algae at a cost approaching viability.
But what if an engineer wants to calculate the enthalpy of a chemical reaction that isn't just a simple combustion?
Like what?
What if they are designing a novel pharmaceutical drug or a new type of lightweight polymer plastic, and they need to know exactly how much heat it will take to form that brand new, entirely unique chemical compound?
Ah, okay. To do that, we move from combustion to the standard enthalpy of formation. This is a very specific metric. It is the exact enthalpy change for a reaction in which exactly 1 mole of a pure substance is formed directly from its fundamental base elements.
And there is a brilliant caveat here.
Yeah.
By absolute mathematical definition, the standard enthalpy of formation of a pure base element in its most stable form is exactly zero.
So oxygen gas O2 is exactly zero.
Solid carbon graphite is exactly zero.
Pure hydrogen gas is exactly zero.
They are the baseline. They are the absolute zero mark on the thermodynamic ruler. Every other complex compound in the universe is measured by how much enthalpy it takes to build it up from those zero-point elemental building blocks.
Which sets the stage for the absolute crown jewel of our entire deep dive. The ultimate culmination of everything we've talked about regarding state functions and mathematical accounting. We are talking about Hess's law.
Hess's law states, if a chemical process can be written as the sum of several distinct stepwise processes, the total enthalpy change of the overall process perfectly equals the sum of the enthalpy changes of the various individual steps.
Let's go back to our mountain analogy to truly grasp this. Remember Mount Kilimanjaro.
Enthalpy is a state function. Your altitude is 5,895 meters, whether you hiked a 40-mile winding path over 5 days or whether you jumped directly out of a helicopter onto the peak.
The specific physical path you took does not matter at all. The final state is identical.
Hess' law is simply applying that path independence directly to chemical reactions.
Let's walk through an actual chemical puzzle to see how this works. Let's say we want to know the enthalpy change of burning solid carbon graphite with oxygen gas to form carbon dioxide, CO2.
You can view this as a direct one-step helicopter drop. 1 mole of carbon plus 1 mole of O2 yields 1 mole of CO2. The measured enthalpy change, the delta H, for this direct route is negative 394 kilojoules.
But what if we take the scenic route? What if we force the reaction to happen in 2 entirely separate steps?
Okay, step 1. You severely restrict the oxygen. You burn the carbon with only half a mole of oxygen. It cannot form CO2. It forms carbon monoxide instead, CO.
The delta H for that specific step is negative 111 kilojoules.
Now, step 2. You take that newly formed carbon monoxide gas and you burn it again with another half mole of oxygen to finally finish the job and form carbon dioxide. The delta H for that second step is negative 283 kilojoules.
And here is the absolute mathematical magic of the universe's ledger. If you physically add the enthalpy of step 1, negative 111, to the enthalpy of step 2, negative 283,
you get exactly negative 394 kilojoules.
the exact same value as the direct one-step route. The math perfectly, flawlessly adds up. The total enthalpy change of the overall reaction is mathematically identical, regardless of whether it physically happens in one single violent step or 2 distinct partial steps.
It's just so elegant.
Let me play devil's advocate here for a second, though.
Sure.
This math is beautiful, yes. But why on earth do we actually need Hess's law? We just spent 10 minutes talking about how incredibly accurate our bomb calorimeters are. Why don't chemists just put every single reaction into a calorimeter and measure it directly in the lab? Why bother doing this algebraic puzzle with stepwise processes at all?
That is a very valid question, and it cuts right to the reality of physical engineering. We absolutely must rely on Hess's law because in the real world, countless chemical reactions are physically impossible to measure directly.
Why impossible?
Well, for several reasons. Some reactions are incredibly slow. They might take months or years to complete, making calorimetry impossible. Some are violently explosive and would just destroy the equipment. But the most common reason is that many reactions yield incredibly messy side products.
Let's go back to our carbon monoxide example. If you want to measure the exact enthalpy of forming only carbon monoxide, you physically can't do it cleanly in a lab.
No, you can't. If you try to burn carbon with limited oxygen, you can't guarantee that every single atom stops at carbon monoxide.
The reaction is chaotic. Some of the carbon will inevitably find more oxygen and fully burn into carbon dioxide. Some of the carbon won't burn at all and will remain as useless soot.
You end up with a messy, toxic soup of soot, CO, and CO2. If you put that mess into a calorimeter, the temperature change you measure is totally useless because you don't know exactly which reaction caused it.
So you can't measure the CO reaction directly. But using Hess's law, you can calculate it perfectly.
You literally treat chemical equations like algebraic variables. You take known, highly reliable, cleanly measured reactions from standard tables like the combustion of pure carbon to CO2 and the combustion of pure CO to CO2.
You mathematically reverse them, multiply them, snap them together like Lego blocks, and you can solve for the enthalpy of the impossible, messy reaction with absolute mathematical certainty.
Right. If you reverse a known chemical equation, you simply flip the positive or negative sign of its delta H. If you need to double the chemical recipe to make the Lego blocks fit, you simply double the delta H.
It grants chemists near omniscience. We can perfectly predict the energetic requirements or the explosive yields of reactions that have never actually been physically performed in human history.
It is the pinnacle of mathematical power over the physical world. It proves that the universe keeps a perfect, unalterable set of books.
We really did start this deep dive with the mundane act of boiling water, and we ended up uncovering the immutable mathematical architecture of reality.
It is a phenomenal system to understand.
So to quickly bring all of these concepts together for you, the listener, we started with the foundational currency of energy, exploring how microscopic kinetic motion dictates our world.
We mapped the mosh pit of heat transfer, proving that energy only flows from the frantic to the sluggish until thermal equilibrium is reached.
We differentiated the intensive fingerprints of matter from the extensive mass of matter, revealing exactly why liquid water, with its stiff hydrogen bonds, acts as a colossal thermal sponge capable of regulating planetary climates.
We looked into the thermal vacuums of endothermic phase changes, understanding how latent heat brutally tears apart solid crystal lattices, melting hundreds of pounds of ice without ever moving the temperature gauge.
And finally, we tracked the physical toll of pressure volume work, the invisible effort required to lift the crushing weight of the Earth's atmosphere, which led us to enthalpy, the ultimate accounting trick that isolates pure heat.
A concept that culminates in Hess's law, proving that in the ledger of the universe, the path taken is utterly irrelevant, only the state matters.
It is a stunning amount of mechanics to absorb. But before we sign off, I know you always have a lingering thought for us to chew on. Building on everything we've discussed today, the algae biofuels, the perfect math of Hess's law, what is the next absolute frontier here? Where do we take this knowledge next?
Well, if we take everything we've learned to its logical extreme, it completely reframes our entire global energy economy. Think about Hess's law. It proves that the physical pathway from point A to point B doesn't matter. The total energy exchange is identical.
Right. The direct helicopter drop versus the winding 40-mile hike.
Exactly. Now look at our current energy systems. Whether we are burning ancient fossil fuels pulled from deep underground, or whether we are harvesting cutting-edge lipid oils from genetically modified algae, we are relying on biological middlemen.
We are waiting on the agonizingly slow, multi-step biological pathway of photosynthesis to capture the sun's radiant energy and store it in high-enthalpy chemical bonds.
We are forcing plants to do the thermochemistry for us.
We are taking the 40-mile biological hike.
We are. But as our mastery of Hess's law and artificial chemistry grows, the next true frontier is asking a radical question. Could we one day entirely bypass the slow biological steps of Hess's law?
Wait, entirely?
Yes. Could we build artificial non-biological architectures, synthetic chemical reactors that pull massive amounts of carbon dioxide directly out of the ambient air and synthesize ultra-high enthalpy liquid fuels instantly, using nothing but concentrated sunlight and pure thermochemistry?
Wow, bypassing the biology entirely to just run the math directly. We wouldn't need a million years of geologic pressure. We wouldn't even need the algae. We just use the direct thermochemical helicopter drop to synthesize perfect fuel.
Exactly. If the path doesn't matter to the universe's ledger, we just need to engineer a faster, more direct path. And understanding enthalpy is the absolute first step to building that future.
That is a staggering thought to leave on. The visible, tangible world of doors opening and cars moving might be the one we actively interact with, but the invisible mathematical ledger of enthalpy is what's actually running the show behind the curtain.
It really is.
And if we can learn to rewrite that ledger directly, bypassing the biology entirely, the possibilities for human engineering are literally boundless. So the very next time you strike a simple wooden match or plug in a rice cooker or turn the key in your ignition, take a second to remember the invisible, flawless mathematical perfection of the energy transfer happening right in front of your eyes. Thank you for joining us on this deep dive. Keep asking questions, keep looking past the visible, and keep exploring the hidden forces that power your world.